All right, everyone, we are back and we are going to get into our problem set 3 solution video. So we have a yo-yo that has the diameter, a mass, and we're asked to find what's the tension in the string, angular acceleration. If the linear acceleration is this, treat the yo-yo as a flat disk. And what this means is that we can use our description that we talked about previously when we were looking at our example of our Frisbee launcher. So why is this important? And we want to kind of deconstruct when we're doing a problem when there's going to be, again, that yo-yo is going to rotate, right? Because you flick the yo-yo, it's going to go down and it's going to rotate in this direction. So we're going to have to define essentially our IgG, so our moment of inertia. So we're going to define the Ig, moment of inertia, as m radius squared over 12. But let's step back. What's our first step? What are some idealizations? Well, we are going to neglect the mass of the spring. We are going to consider the mass of our yo-yo for sure. We're going to have a coordinate system, x, y, and we're going to also have this definition here. What's our next step? We need to draw our free body diagram. So our FBD, free the body from the diagram, or free the body from the surroundings. So our body is our yo-yo. So our yo-yo is going to have basically some weight, where weight is equal to mass times g. We're also going to have right here some tension, basically going in this direction as well. So weight of the yo-yo, it falls. It's going to have some linear acceleration. And again, we're just going to assume that it's going to fall from here. So weight, tension, those are the values. Now we have our kinetic body diagram. In our kinetic body diagram, we are going to draw the kinetics here. So there's going to be some basically angular acceleration, some Ig alpha here. There's also going to be some linear acceleration, mass times the linear acceleration in the y direction, and we already have that value right here. All right, sum of the force, let's go to our critical expressions. Sum of the force in the x direction, none, so that equals 0. Sum of the forces in the y, that's just going to equal to our mass times our acceleration in y, equals minus w plus t in our notation here. Now, let's go ahead and let's just do the sum of the moments about 1. And I'm going to call 1 this location here. So, sum of the moments about 1, in terms of the forces, there's only one. It's going to be minus w times our radius. Excellent. So that's going to be applied there. It's going to be equal to the sum of the kinetic moments. The kinetic moments is going to be Ig alpha minus, because again, we're going in the clockwise. When this drops down, it is going to unwind like this. It's not going to go in the other direction. At least that's our assumption. We'll see if the math works out. And then we are also accelerating in this direction, and there's a moment from that, because this is just a force, and that's also going to be minus m-a-y times radius. Fantastic. So let's go ahead. Let's define these in Mathematica. So I'm going to quit the kernel, make sure everything is cleared. So let's go here. So our mass is equal to 0.1. Our radius is equal to 0.1. Our AY is equal to 1. Our G is equal to 9.8. And let's see, G is equal to that. Weight is equal to mass times G. And that should be it. So let's go ahead. And then we can write out our equations, which we already have here. So let's go ahead. Let's pull up. So let's go ahead and say Fy is equal to mass times AY. Oops, we already defined it. Good, excellent. Which is equal to minus W plus tension. Our M1 is equal to minus W times radius. So that equal to minus Ig. Oops, we need to define Ig. So Ig is equal to mass times radius squared divided by 12. Is that true? Hopefully, yes. Or divided by 2, excuse me. let's go ahead and make sure that that is indeed the case. Yeah, not 12. Excuse me. That is an error. Although I never make any errors. But anyways. So we're going to go ahead and let's define that here. Let's just hide that. So IG times alpha, and then it's going to be minus mass times AY times R. And I'm going to solve FY M1. And there we go. Tension, alpha, we've got it. Fantastic. So let's go to the next question here. So we have a scaffold. So we're going to go back to our scaffold problem that we kind of worked on previously in statics. So there's a little typo here. So our mass is 100 kilograms of our scaffold. Then the wire here is cut. We're asked to solve for the tension of the wire or the angular acceleration. The centroid occurs here. So we're basically at L over 2 with our length being 10 meters. The linear acceleration at this point G, so actually the point G occurs at L over 2. We're given IgG, so we're told here that the angular acceleration here, there is some, actually linear acceleration, excuse me, MAY. So let's go ahead. We are going to ignore the mass of our wires. We're going to ignore any friction. We are going to consider the mass of our beam. We have X, Y coordinate system like so. Let's draw our free body diagram for this particular problem. So we have our beam. Our G is at L over 2, so we have some weight. We also have, we'll deal with that later. There's going to be some tension in the right wire here. So that's our free body diagram. Nothing else is happening. Our kinetic body diagram, we have at G, there's going to be MAY. There's also going to be, as we can imagine, once this wire is cut, we're going to swing down here. So we're going to actually have some angular IG of alpha, and that's going to be in the positive sense. So we could write out, so sum of our forces in the Y equals minus MAY equals minus W plus TR. We also have some of our moments, and I'm going to go about G here. So our sum of the moments about G will be equal to IG alpha, which will be equal to, there's no perpendicular distance between here and here, so we can't deal with that, so it's just going to be equal to T times R, and that's going to be in the positive sense, times our length over 2. Excellent. And I believe that's all. And we can verify that if we wanted to look at the basically acceleration at other locations or at other points, but we can go ahead now and work with this. So I'm going to go ahead and clear everything here. And I'm going to clear everything in here because make sure we're working clear. Click the kernel, local, good. So the mass is equal to 100, gravity equals 9.8. We're going to also be working with here that IG is equal to S times L squared divided by 12. The length of our beam is equal to 10. Let's go ahead and put that down here. Our linear acceleration, AY, is equal to 50. All right. And I think that should be about it. So we'll define that. And in the meantime, we'll set up Fy equals minus M times AY. Set that equal to minus W, which we'll define W equals mass times G, minus W plus TR. Oops. And then we'll have mg equals ig times alpha equals tr times L divided by 2. Whoops, set that double equal. Hopefully this doesn't mess up. Okay, good. Solve Fy mg capital G. And let's see what we got here. And we have a little bit of a typo here and a little error. So actually, our linear acceleration needs to be 5. So if we keep all those same definitions here, and if we go here, we can just reset, redefine, and here's our alpha, here's our tension, and that is it. So we'll see you in the next video. Thanks. Bye.